So, you know that feeling when you have to train a new hire?
Oh, yeah.
Imagine spending an hour showing them the exact sequence of steps to, I don't know, run a complex reporting macro,
Right.
and they make a mistake, you correct them, they finally get it right.
Standard training stuff.
Exactly. But then they come in the next morning, sit down, and make the exact same error. You'd be tearing your hair out.
Oh, absolutely. It's incredibly frustrating.
Well, if you use AI on a daily basis, this is basically your reality.
Yeah, that's a very good point.
Right. I mean, you prompt a deployed agent to write a script or analyze some data, and it makes a logic flaw. You correct it, it fixes the error, you move on.
Mm-hmm.
But then a week later, you give it a similar task, and it walks right into the exact same trap.
It's the classic goldfish memory problem.
Exactly. So in today's deep dive, we are exploring how researchers are finally, thankfully, curing this amnesia.
It's about time, honestly.
Yeah. We've got a stack of state-of-the-art research in front of us today, specifically focusing on a really groundbreaking paper titled EXG, Self-Evolving Agents with Experience Graphs.
Which is a fascinating read.
It really is. We are going to examine how AI is finally transitioning from treating every prompt as just like an isolated event to actively building structured compounding knowledge.
And this is, it's a critical bottleneck in the field right now.
Totally.
Because we have these deployed systems that are capable of synthesizing vast amounts of information, right? They can reason through highly complex logic.
Right. They seem so smart.
They do. But fundamentally, they are what researchers call behaviorally static.
Behaviorally static. Okay, I want to dig into that label for a second.
Okay.
Because if you follow AI, you constantly hear about models getting smarter and smarter. But you're saying the deployed agents we actually interact with are, well, basically stuck in neutral unless the developers intervene.
Yeah, exactly.
Yeah.
Because the distinction here is between training and inference. To permanently update a model's underlying knowledge, traditionally you have to retrain it. You have to update its actual parameters.
Which is huge, right?
It's massively expensive.
Yeah.
Retraining a multi-billion parameter model takes an incredible amount of time and compute.
So you can't just hit a button every time it messes up.
Right. You simply cannot initiate a retraining run every time an AI makes like a minor syntax error in Python.
So we are essentially just relying on workarounds.
Correct. And researchers have attempted to break this cycle using what they call self-evolving agents.
Right.
But the current solutions, they have pretty severe limitations.
Okay, lay them out for me.
So first, you have online methods like the reflection framework.
Reflection with an X, right?
Yes. And in reflection, the agent basically critiques its own output, realizes it made an error, and corrects itself.
But I mean, that sounds like a good thing. It's checking its own work.
Well, it is beneficial for that specific task in that moment, but the reflection is entirely transient.
Oh, I see.
Yeah, it's confined to that single session. Once the task is complete, the lesson it just learned is discarded.
Like waking up in Groundhog Day.
Exactly. Every day is a blank slate.
Wow. Okay, so what's the alternative?
On the flip side, we have offline methods. And these try to accumulate experience across multiple tasks by saving the interactions.
That sounds better.
In theory. The problem there is the structure of the memory itself. It basically saves unstructured trajectories.
What does that mean?
It's just a raw log of the state, the action taken, and the feedback it received.
Okay, so if I'm picturing this, it sounds like taking every single receipt, sticky note, and email you have and just dumping them into a giant cardboard box.
That is the perfect analogy.
Right, so it's technically saved, but finding the specific lesson you need when you face a new problem becomes this massive search operation.
Exactly. Unstructured memory just becomes a hoarder's garage.
A hoarder's garage. I love that.
It really is. And processing that raw pile of data to find a useful pattern requires complex, time-consuming post-processing.
Which is probably way too slow.
Far too slow to use dynamically while the AI is actively generating a response for you.
Okay, so that sets up the problem perfectly. We either have short-term memory that vanishes the moment the window closes,
right,
or long-term memory that is just too chaotic to search in real time.
Yes, and this is exactly where the experience graph, or EXG, comes in.
Okay, so let's get into the solution. What makes EXG different?
Well, the core innovation of EXG is externalizing memory into a highly structured relational format. Instead of keeping that messy, unstructured diary of a past interaction, EXG abstracts that interaction into a clean atomic unit.
They call that a case, right?
Exactly. It's called a case. And from those cases, it builds a graph.
Okay, so let's break down the anatomy of this graph, because if you're listening to this and trying to visualize it, I like to think of a detective's string board.
Oh, I like that.
Yeah, you have the push pins on the cork board, which are the nodes, and the red string connecting them, which are the edges.
That's a great way to picture it.
So what exactly are the push pins in EXG?
So you have three distinct types of nodes here. First, you have golden case nodes, and these represent the successful optimized solutions.
The wins.
Right. Then you have warning case nodes, which represent the failures or flawed logic.
The mistakes. Got it.
And finally, you have task anchor nodes, which is essentially act as organizational hubs.
What do those do?
They group all the related cases that belong to a specific underlying task.
Okay, so the nodes are the raw events, the successes and failures.
Yeah,
But a string board isn't actually useful without the string.
exactly.
So how are these nodes connected to each other?
The edges are where the system's reasoning is actually encoded. So you have contain edges that just link a task anchor to its specific cases.
Basic organization.
Right. Then you have similarity edges, which connect cases across different tasks that are semantically related.
Okay.
But the real breakthrough mechanism here is the correction edge.
The correction edge.
Yeah, these are directed links, and they're specifically labeled as fixed by.
Oh, wait. Fixed by.
Yes. They point directly from a warning case node to the golden case node that eventually resolved the exact issue.
Okay, I want to make sure I'm grasping the actual mechanics of this.
Oh.
Can you walk me through a concrete hypothetical scenario?
Absolutely.
Let's say I ask an agent to write a Python script to scrape a website, and it messes up the pagination logic. Like it writes a loop that just never ends.
Classic mistake.
Right. How does the graph record that?
Okay, so in a standard setup, you'd tell the agent it failed, it would hopefully write a new script, and you'd move on.
And it would forget.
Exactly. But in EXG, that initial failure, the infinite loop, is packaged into a warning case node.
Okay, so it pins that to the board.
Yes. It contains the flawed code and the error state.
Hmm.
Then the eventual successful script you get becomes your golden case node.
And then the string.
The system draws a correction edge pointing directly from that specific infinite loop error to the pagination fix.
Oh, wow. So the graph isn't just remembering that a coding task happened. It is explicitly mapping the relationship between a very specific mistake and its direct solution.
That is the critical distinction. It's a relational representation, and it's created in real time.
Which solves the hoarder's garage problem.
Completely. It's the first graph-based mechanism for self-evolving agents that makes online experience directly and immediately reusable.
Because it's organized.
Right. The graph grows dynamically as the agent works without ever needing to go offline to consolidate all that raw data.
So if the detective has this perfectly organized string board, how do they actually use it?
That's the next big step.
Yeah, because when a new prompt comes in from a user, how does EXG query this graph without just getting completely overwhelmed by all the data on the board?
Good question. When a new task arrives, the system generates what it calls a provisional case.
Provisional case, meaning it's like a blanked template?
Sort of. It doesn't have an answer yet, right? It just
Right.
has the context of your prompt. It then initiates a search of the graph. It first locates relevant task anchor nodes, and then it performs what they call a one-hop expansion.
One-hop expansion, meaning it finds a relevant starting point and then literally only looks at the cases that are exactly one connection away.
Exactly, along those similarity edges.
Okay, that makes sense.
That's the mechanism. It broadens the net just enough to catch relevant historical context, but restricts the search to prevent the system from getting lost in totally unrelated data.
Keep it focused.
Right. And once it gathers this pool of candidate cases, it has to re-rank them to decide what is actually the most relevant.
How does it do that?
This is where it uses both prompt embeddings and, crucially, failure embeddings.
Wait, I need some clarification on failure embeddings.
Sure.
What does that actually look like to the AI? I mean, is it just doing a text match for a specific Python error code like index error, or is it doing something deeper than that?
Oh, it goes much deeper than simple text matching. Standard semantic search, which uses prompt embeddings, might just look for similar topics, like it sees you are asking for a sorting algorithm, so it pulls up past examples of sorting algorithms.
Makes sense.
But a failure embedding encodes the pattern of the mistake itself.
The pattern.
Yes. It evaluates the current problem context to see if it matches the conditions that led to a past failure.
Oh, I see.
It's actively looking for the conceptual trap.
So it's scanning the current prompt to see if it's about to step on a rake it has already stepped on before.
Precisely. That's a great way to put it.
And then what?
Well, once the system ranks these relevant cases, it formats the data into what are called experience hints.
Experience hints.
Yes, and these hints are injected directly into the system prompt for the large language model.
So the model gets them before it even starts thinking.
Exactly. But there is a very strict hierarchy to how these hints are presented.
Like an order of importance.
Right, the absolute highest priority is given to the fixed by hints.
Because those have the solutions.
Yes. If the system detects that the current task matches a past failure, it prioritizes showing the model exactly how that specific failure was corrected in the past.
Okay.
Below that, it provides warning hints of what to avoid, and then finally general golden hints just for context.
Okay, so I have to push back a little here.
Go for it.
Because what you are describing, injecting past context into a prompt, sounds incredibly similar to retrieval augmented generation, or RA.
Ah, yes.
Right. I mean, we've had vector databases and similarity retrieval for a while now. We take relevant documents, we stuff them into the context window, and the AI uses them.
Very true.
So why do we need all this complexity? The nodes, the directed edges, the one-hop expansions. Couldn't a standard database just pull up a document about, say, how to fix pagination loops?
It's a completely fair challenge, and honestly, the authors of the paper anticipated it.
Really? So how did they prove it?
To prove why the graph structure is absolutely necessary, they conducted ablation studies.
Ablation studies.
Yeah.
For those who don't know, that's when you take pieces away.
Yes. An ablation study systematically removes individual components of a system just to isolate their impact on the overall performance.
So they literally turned off different parts of the graph to see what would break.
Exactly. And when they removed the similarity edges, performance dipped a bit.
Okay.
But when they removed the correction edges, those explicit fixed by red strings connecting a failure to its solution,
Well, yeah.
performance just plummeted.
Wait, taking away that single relational link caused a system crash.
It caused a massive drop in accuracy.
Why?
Because without that directed edge, the system is essentially just functioning like the RAG setup you just described.
Oh, I see.
It might retrieve a past failure and it might retrieve a past success, sure. But it hands them to the model as completely isolated pieces of text.
And the model has to figure out the connection.
Exactly. The model has to spend its own reasoning capacity trying to figure out how they actually relate to each other.
Which takes compute and introduces error.
Right. EXG explicitly retrieves the historical repair logic for a specific failure type. It retrieves the I tried X, it failed because of Y, so I did Z.
Got it.
That relational context, that direct link, is the engine of the entire system.
Okay, that makes perfect sense. It's basically the difference between handing someone a textbook and hoping they find the right answer
Right.
versus handing them a highly customized cheat sheet of their own past mistakes and exactly how to fix them.
That is a perfect summary.
So let's talk about the data. We understand the architecture now. But does giving an AI this personalized cheat sheet actually translate into measurable performance gains?
Oh, absolutely. The benchmark results are quite striking, actually.
What do you with the numbers?
So the paper evaluated EXG across two primary domains. First, code generation, using benchmarks like HumanEval and Eval+.
Okay.
And second, multi-hop reasoning, using things like music and Hotpot QA.
Benchmarks.
Very. And they tested it across a whole family of models, from the highly compact Qwen3 1.7b parameter model all the way up to the massive Qwen Max model.
Let's start with the smaller models then, where memory and reasoning capacity are naturally a lot more constrained.
Right. Well, on the HumanEval code generation benchmark, using that tiny Qwen3 1.7b model, implementing EXG improved first attempt success. A metric known as pass at won by over 150% compared to the reflection baseline.
Wait, really? 150% improvement just from restructuring how it accesses its own memory?
Yes.
That is a massive jump. And pass at 1 means it gets the code right on the very first try without needing the user to even tell it there's an error.
Correct. It essentially took a small, efficient model and gave it the compounding, problem-solving ability of a much, much larger one.
That's incredible.
It is. But you know, the metric that is perhaps most disruptive to how we deploy AI isn't even just the accuracy.
What is it?
It's the computational efficiency.
Oh, wait. Explain that. Because usually adding a complex search step slows the system down.
It's counterintuitive, I know. But EXG actually reduced the number of times the system had to call the LLM API. Well, in the baseline self-evolving framework, it took an average of 2.21 LLM calls to resolve a task. With EXG, That dropped to 1.2 calls.
Wow, that is almost cut in half.
It's a 45.7% reduction in API usage.
That's huge for developers.
Absolutely. And consequently, the overall LLM inference latency, which is the time you, the user, sit there waiting for an answer, dropped by up to 30.5%.
And what about the time it takes to do the graph search?
A completely negligible overhead of 18 to 22 milliseconds.
Okay, if I'm doing the math on this, it feels almost magical at first. You're injecting more context into the prompt, you're performing an extra graph search, yet the system is somehow faster and uses fewer tokens.
Right.
But if we tie it back to that pass at one metric, it actually makes perfect sense. It's faster because it avoids the apology loop.
The generate, fail, apologize, regenerate loop.
Yeah, we all know that loop too well.
We really do. Baseline methods like reflection just burn massive amounts of compute. They generate a full, completely incorrect output. Then a verification step runs, realizes the failure, prompts the model to reflect on why it failed, and then forces it to generate a second full output.
Which takes forever and costs a ton.
It is hugely expensive. EXG shifts the compute from generating long, incorrect answers on the back end to providing highly structured preventative guidance on the front end.
It essentially stops the mistake before a single token of bad code is even generated.
Exactly. And the data backs that up emphatically. On the music benchmark, which involves long, complex, multi-hop reasoning chains, EXG reduced output tokens by 84%.
84% fewer tokens generated.
Yeah.
I mean, if you are a business paying for API access by the token, that is an immediate, massive cost reduction right there.
And it only gets better.
I assume this efficiency only improves as the graph gets richer and richer.
You assume correctly. The paper actually tracked the learning curves as the agents tackled sequential tasks, and the contrast is stark.
What did it look like?
Well, the baseline agents, the ones without the graph, would hit a ceiling. After about 60 tasks, their accuracy just plateaued at around 55 to 58%.
They just stopped learning.
They simply stopped improving because their transient memory couldn't compound.
They reached the limit of what they could hold in their short-term context.
Right. But the agents equipped with EXG, their learning curve maintained a steady upward trajectory.
How high did it go?
By the end of the task sequence, they were approaching 80% accuracy.
Wow.
Because their knowledge isn't static. Every new edge case they resolve becomes a permanent, instantly retrievable asset on that relational string board.
So if you're a developer listening to this right now, you might be thinking, this is great theoretical research, but I've already built my entire application on an existing framework.
Right. I don't have the resources to build a custom AI architecture from scratch.
Exactly. So how practical is this to actually deploy? Do you have to rip out the entire foundation of your current setup to use an experience graph?
No, and that is perhaps the most elegant aspect of this whole research. EXG is designed to be highly modular.
Modular?
Yes. It operates entirely at inference time. It is a true plug-and-play module.
Plug-and-play, meaning it acts as middleware. Like you don't have to touch the model's underlying weights at all.
You do not need to retrain or fine-tune the LLM whatsoever.
That is a relief.
The researchers actually demonstrated this by creating variants. They attached the EXG module to the existing reflection framework, creating EXG reflection.
Just snapped it right on.
They attached it to the SE agent framework, too. It basically acts as a wrapper around your existing model.
So how does the flow work then?
It intercepts the user's input, searches the graph, injects the prioritized experience hints into the prompt, sends it to the LLM, and then logs the outcome back into the graph.
Okay, so it's really like handing a heavily annotated study guide to a student right before they take a test.
Exactly.
You aren't altering the student's brain. You are just providing them with vastly superior reference material that is tailored to their known weaknesses.
I love that analogy. And because the memory layer is entirely separated from the reasoning layer, it enables a highly effective offline mode, too.
Oh, offline mode. How does that work?
You can let an agent run through thousands of training tasks in a sandbox environment, just building up a massive, rich experience graph.
Right.
And then you can freeze that graph and deploy it as a static external memory for a brand new deployed agent.
Wait, but how does a frozen graph perform compared to systems designed specifically for offline memory?
Very well, actually. The authors tested this frozen offline mode against a state-of-the-art offline baseline called Expel.
Expel.
Right. And even with a frozen graph, EXG achieved competitive and in many cases superior test stage accuracy.
Really?
Yeah. It recorded higher pass at 1 rates on the Hotpot QA benchmark, all while requiring significantly fewer LLM calls during the data collection phase.
I guess that makes sense because the relational structure, the explicit link between the error and the fix is just inherently more efficient for an AI to parse than trying to deduce logic from a flat database.
Exactly. It's pre-digested logic.
And the modularity means that, a year from now, if a much smarter foundational model is released, you don't lose all the specialized knowledge your current agent hasn't built up.
Precisely. You preserve the experience perfectly.
You just swap the brain.
You simply unplug the old reasoning engine and plug the new, smarter LLM into your existing, highly mature experience graph.
That's awesome.
And the new model immediately benefits from all the edge cases and failures the previous model encountered.
That is just incredibly powerful.
Yeah.
So just to synthesize everything we've unpacked today,
Sure.
we started with the very real workflow frustration of AI's goldfish memory, right? Its tendency to remain behaviorally static and just repeat the same mistakes.
The Groundhog Day effect.
Exactly. Then we explored how the experience graph framework takes the ephemeral trial and error process and cements it into a structured relational graph. We saw how explicitly linking failures to fixes via those correction edges prevents mistakes before they even happen.
Which drastically cuts computational costs and latency.
Right. And finally, we looked at how this plug-and-play modularity allows an AI's intelligence to genuinely compound over time without the need for any expensive retraining.
It really offers a highly practical roadmap for overcoming one of the most stubborn limitations in deploying autonomous agents at scale.
It really does.
But before we conclude today, I do want to leave you with an implication of this architecture that extends a bit beyond what is strictly tested in the paper.
Oh, I always appreciate pulling back to look at the macro view. What are we considering here?
Well, the current research focuses on a single agent building its own localized graph, right?
Right, one agent, one graph.
But because EXG operates entirely outside the model weights as a structured data layer, there is actually nothing preventing the aggregation of these graphs.
Oh, wait, you're talking about merging them?
Exactly. Imagine a near future where thousands of specialized AI agents across the globe are deployed in completely distinct environments.
Like coding, medical diagnostics, supply chain logistics.
Yes. And every time one of these agents encounters a unique edge case, fails, and finds a solution, it instantly updates a massive, shared, global experience graph.
Wow.
What happens to the pace of technological development when the AI assisting you on your laptop instantly learns from a subtle error corrected by an entirely different AI in a lab on the other side of the world just minutes prior?
The compounding effect goes from linear to completely exponential. I mean, the detective's stringboard isn't just in one precinct anymore. It's a global database of corrected logic.
Exactly. And that fundamentally shifts how we think about scaling artificial intelligence globally.
That is a wild thought to end on. Thank you to everyone listening for joining us on this deep dive. As you navigate your own workflows this week, it might be worth considering how you structure your own experience graphs.
Good advice.
How effectively are you linking your own process failures to permanent fixes? Hopefully, unlike the baseline AI we discussed today, you won't find yourself stuck in a loop tomorrow. We will catch you in the next deep dive.